Okay, in this lecture we are going to start what is called electrostatics. Electrostatics. So basically we will be dealing with charges at rest. Okay, static. The word static means at rest. So static implies at rest. So electrostatic means charges at rest. So we are going to deal with a subject where we are going to see the behavior of charges which are at rest. In fact, the problem that we are going to solve in this is, we are given a test charge called Q0. It is a test charge, and there are other charges Q1, Q2, Q3 and Q4, and our idea is we want to find the force on this so-called test charge due to other charges, because once we get this force we can get acceleration, and once we know acceleration we can predict the motion of the test charge. Okay, so the idea is I want to predict the motion of test charge in the presence of other charges. The other charges are Q1, Q2, Q3, Q4 and so on. So as we studied in lower classes, there are two types of charges. One we call as positive, one we call as negative. In fact, we give negative charge to an electron. It is purely convention. We could as well as given positive charge to an electron, but we choose to give it a negative charge. Okay, Mr. J.J. Thomson has chosen to give negative charge to electron, and we follow that convention. Okay, so the whole problem of electrostatics is there are some static charges. All these charges are at rest, and there is this test charge. This test charge can move in general. The test charge can move. So basically, the charge which is experiencing force, this is the charge which is experiencing force. Okay, this can move. Charge which is experiencing force can move. The charge exerting forces, okay, the charges which are exerting forces must be at rest. So these are the charges which are exerting forces. That is the conditions of electrostatics. These are the conditions. The charges which are exerting force must be at rest, and the charge which is experiencing force can move. Why is that? Because if the charges which are exerting force, if they move, we will see later, they also create what is called a magnetic field. Moving charges can also create a magnetic field. We don't want to go into magnetism right now. So the charges which are exerting force must be kept at rest. The charge which is experiencing force can move in general. Okay, so our aim in this topic is to find the force acting on the test charge Q0 because of these charges which are at rest. The charges which are at rest are Q1, Q2, Q3, Q4 and so on. Okay, that is the idea. Okay, but before we do this, this is given by Coulomb's law. So let's investigate why there are two types of charges. In fact, why there are two types of charges, why one positive, one negative. How did people come to this conclusion that there are two types of charges? That is as per what is called the Thales experiment. Thales experiment. What they have done is, they have taken a ebonite rod, and they have rubbed this with what is called fur, and it was found that this ebonite rod gained some charge. Okay, in fact later we found that charge to be negative, and fur gained positive charge. So what happened was, when you rubbed this ebonite rod with fur, some electrons from fur went onto the ebonite. Ebonite is something similar to wood. So some electrons from fur went into the ebonite. So ebonite gained electrons, gained negative charge. Fur lost electrons, it gained positive charge. Two such ebonite rods, which were rubbed with fur, were brought together and they were found to repel. Okay, they were found to repel. They did another experiment where they took a glass rod. So they had a glass rod which they rubbed with silk. Now in such a case, surprisingly, glass rod gains positive charge, silk gains negative charge. In fact, the rule is, whichever material is hard, it will gain electrons. Whichever material is soft, it will lose electrons. Silk is a fairly hard material, so it gained electrons. Whereas fur is a loose material, it lost electrons. Now when they brought two such glass rods, they also repelled. So they thought there is something called charge, which is also there on ebonite rubbed with fur, which is also there on glass rod rubbed with silk. Okay, and these charges repel. That is what they came to the conclusion. But they did not only that. They brought this ebonite and this glass rod together and they were found to attract. If they repelled, the charge on ebonite and glass rod would have been of same type. But since it attracted, it should be of different type. Okay, if it is same type, it should repel. But if it is of different type, so the glass rod and ebonite rod, which are charged, attract. From this experiment, they came to the conclusion that there are two types of charges, one positive and other negative. Okay, that is how they came to the conclusion using this experiment. This is the process of charging by friction. When you rub two bodies, because of friction, electrons go from one object to another object. So this is the process of charging by friction. There is another process of charging which is called charging by induction. Okay, so you can charge a body using two ways. One is charging by friction, the other is charging by induction. Induction, to induce, to bring about, induce sleep. For example, I can induce sleep in you. I can bring sleep in you by doing some hypnotism, let us say. Similarly, I bring charge in a body using induction. How do I do this? Okay. Let us say I have a metallic object. This is a metallic object. And I bring a rod, let us say a glass rod, which is positively charged near this metallic object. Metals contain lots of free electrons which can move here and there. In fact, every atom of a metal contributes to one or two free electrons. The outermost electrons in a metal atom, they can go here and there and come back. They can take a walk in the park. So if each atom of metal contributes to one or two free electrons, there are of course millions of atoms in a metal object. So you'll have millions of electrons which are free, in the sense they can move. So these free electrons get attracted by the positive charge on this glass rod, and the positive charges would get repelled. So there is a forcible separation of charges in a metal when you bring a glass rod which is charged near the metal. Why this separation is happening? Because the electrons in the metal get attracted towards the positive charge on the glass rod. They come nearer, and the side which has less electrons is deficient in electrons. There is a positive charge there. The positive charge is that of the nucleus. Now if I connect this metal by a wire to earth, if I connect it to ground, all these positive charges, okay, they would run away to earth. These positive charges would run away to earth. This is what happens. So the metal will ultimately be left with only negative charges. So without rubbing the metal, I was able to charge the metal. The metal was initially neutral, now I brought negative charge onto the metal. So this is the way to charge a metal using induction. Of course, you might ask a question, why only positive charges go into earth? We will discuss about that a little later once we go into more advanced concepts of electrostatics. Of course, if you have a different situation where instead of a glass rod, let us say I have, let me use the same green color. So instead of glass rod, I have the ebonite rod which is negatively charged, and I brought a metal. So this side will be positive because this negative charge repels electrons, that side will be negative. Now if I connect this to earth, these negative charges will in fact now go to earth. Okay, so always the charge on the metal will be opposite to the charge on the rod. If you bring a glass rod with positive charge, charge on the metal will be negative after you connect it to earth. If you bring an ebonite rod with negative charge, charge on the metal will be positive after you connect to earth. Okay, why this happens we will see this later, but you must understand this process of charging by induction. That is the most important thing. So we can charge a body in two ways. One is by friction, other is by induction. This induction is typically possible in metals. Okay, it is very difficult to induce charges in non-metals, but in metals induction is readily available because electrons, there are many free electrons in a metal which can move here and there. So induction is possible in metals. So we will discuss this Coulomb's law. In fact, this is the law which gives us the expression for force between two charges. So I have 2 point charges, one of charge Q1, other of charge Q2. Okay, generally charge is measured in coulombs. The unit of charge is coulomb, on the name of this great scientist Coulomb, and this law is also Coulomb's law given by Coulomb. So we have 2 point charges. What is a point charge? A charge which occupies zero size, point sized charge. Charge which does not occupy any volume is called point charge. So our Coulomb's law is valid only for point charges. That we must remember. Coulomb's law is valid only for point charges. So we have these 2 point charges Q1 and Q2 separated by a distance r. Okay, Q1 and Q2 separated by a distance r, and I want to find the force of attraction or repulsion between these 2 charges. Remember, if both Q1 and Q2 are positive, the force will be repulsive. Even if both are negative, the force will be repulsive. If one of them is positive and other negative, the force will be attractive. That is the idea. Okay. Now, first I will tell you some properties about this force. Right now I will assume both the charges are positive. Both Q1 and Q2 are positive. So here Q1 will repel Q2 in that direction. Okay. And Q2 will also repel Q1 in that direction. Okay, you can see that this force of repulsion is along the line joining the charges. So if you want the directions of this force, you must first join the charges by certain line. The forces will be along this line. Okay, what I mean by that is the force will never be in this direction and that direction. They must be along the line joining the charges. That is the rule. Okay, then you see the force is on both the charges. Q1 will repel Q2, Q2 will repel Q1. These are what is called action reaction pairs. These charges are action reaction pairs. Okay, that is the idea. So the magnitude of both these forces is same. So if Q1 repels Q2 with 10 newtons, Q2 must also repel Q1 with 10 newtons, because action and reaction pair have the same magnitude, and these forces have opposite directions, which you can see. Okay, these forces have opposite directions, and not only that, these forces act on different bodies. That is the most important point. Action and reaction pair never act on same body. That's a rule. Okay, for example, the force on Q1, if you call it action, then reaction acts on Q2, not on Q1. Okay, so action and reaction pair act on different bodies. Okay, now let us first write the magnitude of this force between these two charges. F, the magnitude of force between these charges. When I say between these charges, this force is also on Q2, it is also acting on Q1. The force on Q2 is due to Q1, the force on Q1 is due to Q2. Okay, in fact, for there to be a force, there must be two objects. That is the rule. Okay, the interaction between two objects is called a force. So we must have the magnitude of this force is given by some constant into Q1 into Q2 by R square. This is the magnitude of the force acting on charge Q2. It is also the magnitude of force acting on charge Q1. Okay, you can see this is similar to gravitation. The force is proportional to the product of the two charges. It is inversely proportional to square of distance between them. Okay, so the force on Q1 depends on both the charges Q1 and Q2. Similarly, the force on Q2 also depends on both the charges Q1 and Q2, and the force also depends on the distance between them. It is inversely proportional to the square of the distance. That's why this Coulomb's law, electrostatic force of attraction or repulsion, given by Coulomb's law, and gravitational force given by Newton's law of gravitation, these are called inverse square law forces. They follow the inverse square law because these forces vary as 1 by r square. Here k is a constant, okay, which is not exactly absolute constant like gravitation. This constant k, the value of k here in electrostatics depends on medium. Okay, for example, generally we write this k as 1 by 4 pi epsilon naught for vacuum, and its value is 9 into 10 power 9 newtons. Okay, the value of k, if the charges are in vacuum, is given by 9 into 10 power 9. Sorry, it's not Newton. The value of k is Newton meter square per Coulomb square. Okay, Newton meter square per Coulomb square. That's the unit. Newton meter square per Coulomb square. That's the unit of k. K is sometimes written as 1 by 4 pi epsilon naught. So I can write the magnitude of this force as 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay. Now this epsilon naught, it is called permittivity of free space. Epsilon naught is called permittivity of free space. That means the charges are placed in space, in vacuum. Okay, if you place them in some other medium, this constant value will change. In such a case, we write this constant as 1 by 4 pi epsilon. We do not write epsilon naught. Epsilon naught or epsilon 0 would refer to vacuum. It means the charges are placed in vacuum, in free space. So for any other medium, instead of 1 by 4 pi epsilon 0, we write 1 by 4 pi epsilon. Epsilon will be permittivity of that medium. Okay, so is that clear? For any other medium, the constant is written as 1 by 4 pi epsilon. Epsilon is permittivity of that medium, in whichever medium the charges are placed. Okay, that is the idea. That is the idea of this law. Of course, this is not exactly Coulomb's law, because I have given only the magnitude of force. When I say force, I must even tell the direction. So I must write the correct Coulomb's law by writing force as a vector. Okay, so we will discuss about this vector nature of Coulomb's law now. So in this section we will see the Coulomb's law in vector form. In fact, if you write Coulomb's law in vector form, only then it is called Coulomb's law. Previously what we wrote is not Coulomb's law, because it is only giving you the magnitude of force. So here, for example, we are only writing the magnitude of force. Now we will see how to write Coulomb's law in vector form. Okay, suppose if I have 2 point charges, one is q1, other is q2, and the distance between them is d. I will define 2 vectors. One vector is what is called r12. So I can say this is, I beg your pardon, this must be written as r21. So this is actually position vector of 2 with respect to 1. That means if I stand at 1, if I stand at the location of the charge q1, and if I draw a position to q2, it gives me position vector of 2 with respect to 1. Similarly, I can even define what is called position vector of 1 with respect to 2. Okay. Now clearly from this diagram you can see that r12 is nothing but minus of r21. Okay. Both vectors have same magnitude d but have opposite directions, so I can write that. So now I can write Coulomb's law in vector form. If I assume these 2 charges are positive, if I assume that, actually I need not assume that, the law that I am going to write is most general, but for a minute let us assume these 2 charges are positive, then the force on q2 will be repulsive in nature, like that. Force on q1 will also be repulsive in nature. So in such a case I can write force on 1 due to 2. Okay, force on charge 1 is given by 1 by 4 pi epsilon naught, okay, q1 q2 by r12 cube into the vector r12. Is it clear? So I'll just write it at the side. So force on 1 due to 2 is given by 1 by 4 pi epsilon naught q1 q2 by r12 cube into r12. Can you see that? Actually it should have been q1 q2 by r12 square, but in the numerator and denominator I multiply by another r12 and write the numerator as a vector. You can see force on 1 due to 2, force on charge 1 due to 2 is to the left. Okay, it is to the left. In fact, it has a direction of r12. I can see this from the law. Similarly, I can write force on 2 due to 1 is that constant 1 by 4 pi epsilon naught, which I write as k q1 q2 by R21 cube into R21. So this gives us Coulomb's law in vector form. Sometimes this same law is also written like this. It is written as F12 is K Q1 Q2 unit vector R12 by R12 square. Both mean the same thing. Okay, all these are different forms of writing the same law. Now let me explain this expression for force, what I have written here, is valid irrespective of the type of charges. Which means if you have both the charges as positive, still this is valid. If you have both the charges as negative, still this is valid. If you have one positive, one negative, still this is valid. Let us see how it is valid in all cases. First, if both the charges are positive, then force on Q1 is repulsive and is to the left, as I have shown in the diagram. So force on Q1 will be to the left in the direction of R12, and you can see that F12 has same direction as R12 because both these Q1 and Q2 are positive, so net result will be positive. So the direction of F12 will be same as R12. Then if both are negative, again force will be repulsive. So when I substitute into the star, the expression which I have marked as star, both Q1 and Q2 are negative, but their product will be positive. So again F12 has same direction as R12. Now if one charge were positive and other were negative, the force would have been attractive. In such a case, the force on Q1 will be to the right, as I am showing by the green line. In such a case, this product Q1 into Q2 will be negative. Because one of the charges is negative. So direction of F12 is minus R12. Can you see that? R12 is to the left, whereas force is to the right. The force is attractive, as shown by the green arrow here, which I am showing here. So this law, what I have written here in vector form, is most general. It is valid for any type of charge. Okay, that is the interesting point of this Coulomb's law in vector form. Okay, this law is valid irrespective of the so-called magnitude of, the type of these charges. Why this Coulomb's law in vector form is necessary? In fact, Coulomb's law gives force between two charged particles. Force is a vector quantity, so we must write this law as a vector. What we wrote previously here, okay, this is not Coulomb's law. It is only giving you the magnitude of force, right? So actual Coulomb's law is what is I have marked by star. That is actual Coulomb's law. Now let us see some questions based on this Coulomb's law. Some simple questions. Okay, so I will erase these two slides. Suppose I have two charges, both of same magnitude. If I keep a third charge in between, net force on this will be 0. Net force will be 0. Okay, because these two charges will equally exert force on this capital Q. They will equally exert force. The force may be attractive or repulsive, but they will equally exert force. So net force on Q will be 0. Similarly, if I have three charges in the form of an equilateral triangle, like this, three charges at the corners of an equilateral triangle. If I keep a capital charge Q at the centroid of this triangle, net force on the central charge will be 0, because all these charges will equally pull that charge. Similarly, if I have four charges at the corners of a square, okay, Q, 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 if I keep a capital Q at center, net force on the capital Q will be 0. So I can generalize this rule. N charges which are at the corners of a regular polygon exert no charge on the central charge q. Is that clear? If I have n charges small q equally distributed in space, okay, forming a regular polygon, then they exert zero force on a charge which is placed at the center of the polygon. So they exert zero force on this central charge, because all these charges will equally pull this or push it. Okay, so net force will be 0. So based on this, let us see one question. Suppose I have a regular pentagon and at the 4 corners I have 4 charges. Okay, like that, and 5th corner is empty. Okay, and at the center I am placing a charge capital Q. These 4 charges are small q. This corner is empty. Now this is the regular pentagon, and the distance of the central charge from each corner, this distance is A. The distance is A. So we have to find net force on the central charge due to the remaining 4 charges. This is the question. So how to solve this? See, if there were 5 charges totally, force would have been 0. If there was also a 5th charge at the corner, empty corner, the force would have been 0. So I can write force due to 4 charges plus force due to 5th charge totally. The total force will be 0. So I can write force due to the remaining 4 charges is negative of force due to 5th charge. Negative of force due to 5th charge. So what I must do is, if I want to calculate force due to these 4 charges, first find force due to the 5th charge. If I place it, put a minus sign in front of the force, means reverse the direction. Then you will get force due to the 4 charges. That's the idea. Now what will be the force due to 5th charge? It will be K Q into Q by A square, simply. Okay, the force may be attractive or repulsive depending on the signs of capital Q and small q, whatever it is. Suppose if the force on capital Q is attractive, if it is like that, then force due to remaining 4 charges must be repulsive. I mean in that direction, in the opposite direction. Why? From here you can see force due to 4 charges is minus of force due to the 5th charge. So this is one way to do the problem. Or other way is simultaneously put plus q and minus q at the empty corner. Putting plus q and minus q simultaneously at the empty corner is as good as putting no charge, because plus and minus q will cancel. So now the force due to these 5 charges, all plus q's, is 0. So what remains is only the force due to minus q on capital Q. So we have to find the force on capital Q due to only minus q, and that is in magnitude KQQ by A square. So that is the answer. So that's a very neat, simple question. Okay. Now in this problem we have assumed one very important thing, which is called principle of superposition. What this says is, if I have certain test charge Q0, and if there are charges Q1, Q2, Q3, Q4, etc., then principle of superposition says that the force on test charge, which is Q0, due to Q1 is not influenced by the presence of Q2, Q3 and Q4. That means if Q2, Q3, Q4 were not there, if they were not there, if Q1 exerts 10 Newton force on Q0, then even if Q2, Q3, Q4 are there, still Q1 exerts 10 Newtons only on Q0. That means the force on Q0 due to Q1 is not dependent on the presence of other charges. Remember, I am talking about force on Q0 due to Q1 alone. So the force on Q0 due to Q1 alone is independent of whether other charges are present or not. Okay? So presence of other charges will not change the force exerted by one particular charge on another. This is the principle of superposition. So we assume this is true, and in fact it is true, and proceed with our problem of electrostatics. Okay, now let's see another problem. Suppose there is a charge Q here and there is a charge Q here, and both are separated by certain distance, let us say d. Now on this perpendicular bisector, I want to place a capital Q at certain distance x in such a way that force on capital Q is maximum. Okay, I want to place a charge capital Q at a distance x from the center. This is the center, such that force on capital Q is maximum. We have to find x. That means at what distance on the perpendicular bisector should I place a charge capital Q so that force on this capital Q due to the two charges small q's is maximum. This we have to find. This is the question. Let us see how to solve this. If I put this Q at center itself, what is the force? Force on Q is 0. Okay, if I put the charge at center, both will equally attract or repel. So force will be 0. Similarly, if I put Q at infinity, if I put capital Q at infinity, the force exerted by both the charges, remember, kq into q by infinity square, this will be 0. So force exerted by each charge will be 0 if I place capital Q at infinity. So you see, if I take this capital Q from center to infinity, at center force is 0, at infinity also force is 0. So when I take this capital Q from center to infinity, force is going from 0 to 0. So at center force is 0. As I take Q upwards, force increases. At certain point force is maximum. Then it decreases and becomes 0 at infinity. So in fact, if I plot a graph between force and the x, when x is 0, force is 0, then force increases, and finally force will go to infinity, 0 at infinity. Okay, so it is like this. It is going to 0 at infinity. So somewhere the force is maximum at certain value x naught. We have to find x naught. In fact, at that point, if you draw a tangent, slope of the tangent is 0, and slope of the tangent is given by derivative of f with respect to x. That must be 0 at this point called x naught. So how to find this x naught? First, let us find force on capital Q at the distance x. This charge will also exert a force. Okay, this charge will also exert a force. I am assuming force is repulsive. Only vertical components of these forces add. Horizontal components do not add. They cancel. Okay, so net force, I can write it as, first let us find force due to one charge, that is given by kqq by 4 pi epsilon naught. What is distance between small q and capital Q? X square plus d by 2 whole square under root. That is the distance. Can you see that? By Pythagoras theorem, this is root of x square plus d by 2 whole square. So k q by 4 pi epsilon naught distance square will give me x square plus d by 2 whole square. So that's the force on capital Q due to one of the charges. But we must take only vertical component of this force. Okay, we must, because when we add, horizontal components cancel. So I must take only the vertical component, cos theta. Clearly cos theta is given by adjacent by hypotenuse. So cos theta is given by x by root of x square plus, okay, x square plus d by 2 whole square. Okay, this term is nothing but cos theta, only vertical component. Two such vertical components are there, one due to the left charge small q, one due to the right charge small q, so 2 times. So this is the force on capital Q. Now we have to find the distance x at which this force is maximum. So we must take derivative of f with respect to x and equate it to 0. Okay, so let's do that on the next page. So I must have d by dx of the force should be equated to 0. What is the force? 2kqqx 2kqqx by 4 pi epsilon naught x square plus d by 2 whole square whole power 3 by 2. The denominator, see carefully, you have power 1, power half, both get added and become power 3 by 2. So x square plus d by 2 whole square whole power 3 by 2. So we must take derivative of this. Actually we are taking derivative of the variable x. So all other terms which are constants, you can separate them out of the derivative. So we must use u by v rule when taking derivative. So when we use that u by v rule, it becomes like this: x square plus d square by, d by 2 whole square, d by 2 whole square whole cube. First we must square the denominator, then denominator into differentiation of numerator. What is numerator? X. Differentiation of numerator is 1 minus numerator into differentiation of denominator will be 3 by 2 x square plus d by 2 whole square whole power 3 by 2 minus 1 into derivative of inner term, which is 2x by chain rule. So this must be equated to 0. So if you carefully simplify, numerator will become x square, we can forget about denominator, it goes to the other side and becomes 0. So numerator will become x square plus d by 2 whole square under root, I will take common, into x square plus d square by 4 minus 3x square. This must be 0. So from here I can get x as plus or minus d by 2 root 2. So I get two values of x at which force is maximum. One is plus 2 root 2, that is above at a distance of d by 2 root 2. One is d by minus 2 root 2, which is below. Here also somewhere force will be maximum. Okay, you can take the capital Q like this, or you can take it down also. So at a distance of minus d by 2 root 2 also, from the center on this perpendicular bisector, force is maximum. So we have plus d by 2 root 2 and minus d by 2 root 2. Okay, clear? So in the next session we will take some more problems on electrostatics and then go into electric field. Okay, thank you.